Hello and welcome back to the deep dive. Today we're heading straight into the chemistry lab. We're focusing on a really specific but very important topic from Unit 9, amines.
Yes, we're going to be decoding the chemical reactions of diazonium salts.
And if you're a Class 12 student, this is one of those topics that can, practically guarantee you marks if you just get the logic right.
Oh, it's definitely a high-scoring topic. And more than that, it's one of the few places in organic chemistry where you actually see something dramatic happen. It's not just mixing two clear liquids.
Exactly. And that's where I want to start. I want you to just for a moment visualize you're in the chemistry practicals.
The tension is high, the external is watching.
Right. And you're at your workbench with a test tube. It's got this clear, ice-cold liquid inside. You add something to it, and poof, magic.
It really does feel like a magic trick.
You might see this sudden, vigorous fizzing, like, bubbles just erupting.
Yeah.
Or you might see a brilliant orange or bright red solid just appear out of nowhere.
And those two things you just said, the bubbles and the bright color, that's basically the whole topic in a nutshell.
Really?
Yes. The bubbles are nitrogen gas escaping, and that bright color is an azo dye being formed.
Okay, so our mission today is to understand the chemistry behind those bubbles and colors. But first, why should we care? I mean, beyond the practical exam.
Well, scientifically, diazonium salts are like a master key for the benzene ring. You know how benzene is very stable, it doesn't like to change its groups easily?
Right, it's very inert.
But diazonium salts let us swap groups on that ring like we're changing parts in a machine. Without this chemistry, we wouldn't have most of the dyes in our clothes, and making many important medicines would be so much harder.
So it's a tool for molecular precision. Okay, let's start from level 0. What exactly is a diazonium salt?
Okay, at the simplest level, imagine an aromatic amine, like aniline, is a car.
Okay, aniline is the car.
Now, this car has a passenger attached to it. That passenger is the diazonium group. We write it as minus N2 plus N and an N2 plus dollar. It's two nitrogen atoms bonded together.
So the benzene ring is the car, and this N and dollar plus dog group is the passenger.
Correct. But here's the critical part. This passenger is very, very unstable. It does not want to be there.
Why not?
Because nitrogen gas, N2, is one of those stable things in nature. It loves being a gas. And here we forced it to sit on this ring. It's like a tightly coiled spring, just vibrating and waiting to pop off.
So it's under a lot of tension.
Immense tension. The bond holding it to the ring is very weak. The moment it gets a chance, it meets a catalyst or something, it just jumps off.
And when it jumps off, those are the bubbles we see.
Those are the bubbles. It leaves as nitrogen gas, and that leaves an empty seat on the benzene ring for a new group to come and sit down.
I really like that image. The passenger jumps out, the seat's empty, and someone else quickly grabs it.
Precisely. Now, in chemistry terms, because this group is positively charged and wants to leave so badly, we call the diazonium salt a highly reactive electrophile.
Okay, I want to pause there, because this, I think, is where a lot of students get confused. Usually with benzene, we talk about electrophilic aromatic substitution, where the ring itself attacks an electrophile.
You are absolutely right. This is the biggest misunderstanding trigger. Students are so used to thinking of the benzene ring as electron-rich, as a nucleophile.
But here it's different.
Here, the situation is completely flipped, because that diazonium group, the N2R plus dollar, has a positive charge. It actually pulls electrons away from the ring. So in this specific case, the diazonium salt itself is the electrophile. It's the one that gets attacked by nucleophiles.
So the roles are reversed. That's a very, very important distinction to make.
It is. The nitrogen group is basically shouting, "I'm leaving. Who wants my spot?"
Let's make this even clearer with an analogy. The notes mention molecular musical chairs. How does that work?
It's a perfect analogy for the substitution reactions. So imagine the diazonium group is the person sitting in the chair. The chair is the benzene ring.
Okay.
And circling around the chair are the other players. These are your nucleophiles. Maybe a chloride ion, a bromide ion,
So they're just waiting for an opening.
Exactly. Then we add a catalyst, like a copper salt. That's like the music stopping. The moment the music stops, the diazonium group gets up and leaves. It just flies away as nitrogen gas.
And the chair is empty.
For a fraction of a second, yes.
Yeah.
And because that chloride ion is right there, it immediately sits down. And there you have it. You've swapped the nitrogen for chlorine. You've played musical chairs with molecules.
That makes it so much clearer. But I have a question. Why do we need to do all this? If I want to put chlorine on a benzene ring, why can't I just take aniline and add chlorine directly? Why this middle step?
That is a brilliant question, and it gets to the heart of why this concept exists. You might think, just add chlorine to aniline, it's reactive. But the problem is, aniline is too reactive.
Too reactive? How can something be too reactive?
The aniline group activates the ring so much that if you add chlorine, it won't go to just one spot. It'll attack here, there, everywhere. You get a complete mess of products. It's like trying to use a shotgun when you need a sniper rifle.
Ah, I see. So direct chlorination is messy, uncontrolled.
Exactly. Converting aniline to a diazonium salt first is it's like taming the ring.
Yep.
It allows us to remove the nitrogen and place exactly one group, just one exactly where we want it. It gives us control.
It turns the shotgun into a sniper rifle.
Perfect analogy. And it lets us do things that are otherwise almost impossible, like putting a cyanide group or an iodine atom onto a benzene ring. You can't do that directly, but with diazonium salts, it's easy.
Okay, let's try to create a mental movie for everyone listening. If you're in a safe place, maybe just close your eyes for a moment.
Okay, picture the diazonium group, that NWPIT plus dollar, as a bright red vibrating sphere attached to the benzene ring. It's glowing red because it's so unstable.
A vibrating red sphere, got it.
And on this sphere, there's a countdown clock. It's ticking down. That's because the molecule is thermally unstable. We have to keep it in an ice bath, between 0 and 5 degrees, just to pause that clock.
Right, if it gets warm, it just falls apart.
Exactly. Now imagine two pathways branching out. Path 1. A copper salt comes close, boom. The red sphere flies off as bubbles. That's the gas. And a blue sphere, let's say chlorine takes its spot.
Bubbles and a swap. That's path 1.
Path 2. Another whole molecule approaches, like a phenol ring. This time, instead of flying off, the red sphere grabs onto the new ring. It connects them like a bridge. And the whole thing instantly flashes bright orange.
That's the coupling reaction.
That's the coupling reaction. Bubbles for swapping, orange flash for linking. A great mental anchor.
It is. Okay, let's get into the specifics now. The first one, which you see in every exam paper, is the Sandmeyer reaction.
Ah, yes, the Sandmeyer reaction. A guaranteed guest. Here, we use copper eye salts, so that's EuCl or Kubri, dissolved in the right acid.
So we take our cold diazonium solution, we add the copper salt solution. What do we see?
You immediately see that vigorous bubbling. That is the nitrogen gas, the N2 escaping. It's the passenger jumping out of the car. And when the fizzing stops, you're left with your product, chlorobenzene or bromobenzene.
Now, there's another one that sounds very similar. The Gatterman reaction. What's the difference?
Very similar, yes. The product is the same. The only difference is the reagent. In Sandmeyer, we use the copper salt.
Like copper chloride.
Correct. In Gatterman, we use copper powder in the acid.
Okay, that's an easy distinction. Sandmeyer is salt. Gatterman is powder.
Exactly that. Sandmeyer generally gives a better yield, but for the exam, just remember, salt versus powder.
What if we want to add iodine? Is that also a Sandmeyer reaction?
No, and this is a special case. For iodine, the reaction is so easy you don't even need a catalyst. You just add some potassium iodide, Ki, and warm it a little bit.
Let me guess. Bubbles.
Of course, nitrogen gas has always evolved in these displacement reactions.
Okay, let's talk about what happens if we mess up. You mentioned that countdown clock and the ice bath. What happens if we let the solution get warm by itself?
Ah, that is the hydrolysis reaction. If you take the diazonium salt and just warm it with water, or if you just let your ice bath melt, the nitrogen gas will leave and an AOH group from the water will take its place.
So you end up with phenol.
Yes, you convert the diazonium salt into phenol. It's a proper method to prepare phenol, but in the lab, it's often an accident.
Warm water equals phenol. Got it.
Correct.
There's one more displacement that I find fascinating, the one that acts like an eraser. Can you explain the reaction with hypophosphorus acid?
Yes, a very powerful tool. So suppose you have an amine group. You used it to direct some other groups on the ring, but now you don't want it anymore. You want to remove it.
You just want to go back to plain old benzene.
Exactly. You treat the diazonium salt with hypophosphorus acid, that's 3,3-PO2-2, or even just ethanol. These are mild reducing agents. And what they do is they replace the entire diazonium group with just a hydrogen atom.
So the nitrogen bubbles away and a hydrogen takes its place. It's like the amine group was never even there.
It's a functional group eraser. It turns the salt back into pure benzene. Very, very useful in multi-step synthesis.
Okay, so those are all the bubble reactions. Now for the bridge reactions, the coupling reactions, this is where the color comes from.
Yes. This is the big technology application. This is how we make azo dyes. And in these reactions, remember, the nitrogen does not leave. It stays.
How does that work?
We take our diazonium salt and react it with another aromatic ring that is very electron-rich, something like phenol or aniline. The diazonium ion, which is our electrophile, attacks the phenol ring.
And it forms a bond.
It forms a bridge. The two nitrogen atoms stay in the middle, creating a -N double bond N minus NNN, linking the two benzene rings together.
And this new big structure is what creates the color.
Yes, that long, extended system of double bonds, it absorbs light in the visible part of the spectrum. So instantly, the solution turns bright orange or red.
That's the magic trick from the start.
That is the one.
So just to be crystal clear, if the nitrogen leaves as gas, it's substitution. And if the nitrogen stays and forms a bridge, it's coupling.
That is the golden rule, yes. Bubbles mean substitution. Color means coupling.
We've covered a lot. For the students listening, let's just nail this down with some exam-safe clarity lines. The key sentences you must have in your head.
Let's do it.
Okay, clarity line 1 for Sandmeyer.
Clarity line 1. In Sandmeyer reactions, we use copper, I's, salts like QCl or Q-bar to replace the nitrogen group. This releases nitrogen gas.
And the tieback.
Always mention the bubbles. The evolution of N2 gas is the key observation.
Good point. Clarity line 2, Gatterman.
Clarity line 2. The Gatterman reaction is similar to Sandmeyer, but uses copper powder and acid instead of the salt.
Simple enough. Salt versus powder. Okay, clarity line 3, the accident with water.
Clarity line 3. If you warm the diazonium salt with water, it undergoes hydrolysis to form phenol and releases nitrogen gas.
And the tieback is? Be careful with the temperature.
Exactly.
Clarity line 4, the eraser.
Clarity line 4. We can remove the diazonium group entirely by using hypophosphorus acid, VH3PO2, or ethanol. This reduces the salt to benzene.
Tieback. Think of it as erasing the functional group.
Yes.
And finally, clarity line 5, the colorful one.
Clarity line 5. In coupling reactions, the nitrogen is retained. It forms a bridge between two rings. This creates colored isodyes.
And the tieback, if the question mentions color, you have to be thinking coupling.
Absolutely. And just a small tip, the coupling usually happens at the para position of the second ring. It's a bulky reaction. It needs space.
That's a great tip for getting full marks.
Every little bit helps.
We're almost at the end of our deep dive. Let's do a quick short summary to tie it all together.
Okay, so the core idea is that diazonium salts are unstable intermediates. The nitrogen group is that passenger just waiting to leave.
Our analogy was molecular musical chairs. Nitrogen leaves as a gas, and a new group sits in the empty chair.
The main example to remember is the Sandmeyer reaction using copper salts to swap in chlorine or bromine. Remember them bubbles.
And for the coupling reaction, remember the nitrogen stays, forms a bridge, and you get the bright colors of azo dyes.
And the final point. This is the best way to convert aniline into almost anything else. It gives us that sniper rifle precision on the benzene ring.
I think that covers it perfectly. Next time I see a bright red t-shirt, I'm going to be thinking about those nitrogen bridges.
And when you're in the exam hall, just visualize that bubbling test tube. It really helps you remember the products.
Bubbles and bridges, that's the mantra. Thank you so much for guiding us through this.
It was my pleasure. Good luck to all the students out there with their preparation.
And to all of you listening, keep visualizing, keep learning, and don't let those unstable passengers stress you out. We will catch you in the next deep dive. Goodbye.